Good morning everyone to today's lecture. In today's video we'll be discussing the topic of kinetic energy and work energy theorem and some questions. So what is kinetic energy if we were to define this term? So kinetic energy is energy associated with the system of particles or bodies by virtue of their motion, by which we mean that, let's say, if a body is moving from one point to another, then we say that if it's moving with some speed, let's say v, then we say that some energy is associated with that body. For example, a batsman hits a ball, then if the ball is being hit with some low speed, then the ball is said to be having some low energy associated with it. And if the ball is hit with a very high speed, then we say some high energy associated with the ball. So what is that energy which we are trying to associate it with it or give to that particular thing? In the same way, let's say I have a car and the car is going from one point to another, and it was going with the speed of some, let's say, 20 kilometers per hour. Now I increase the speed of the car to 80 kilometers per hour. Then I would say the car is going in much more energetic fashion. So that particular energy which I am associated with the car because its speed has increased, or if I am loading more material in the car and it is now going with some speed, then we say that its energy is increasing. So that particular energy which we are talking about is called kinetic energy. So kinetic energy, like I said, it is defined as the energy associated with the body by virtue of its motion, and its expression can be written as half mv square. So that is the expression which we remember from our classes already, which we know that the expression of kinetic energy is half mv square and what is our units and so on. So to mathematically define kinetic energy, I can say it is simply half n v dot v or half n v square. So this is the expression of kinetic energy. So let us do some question to demonstrate this expression, the simple expression, which you already know. So let us take the first example or question of a projectile. So I have a projectile which I am projecting with some velocity, with some speed v, on a horizontal plane or on ground. So I am projecting this projectile with some mass m, with some speed v at an angle theta. Now what I have done is that I am again projecting the same projectile at an angle 90 minus theta. At some 90 minus theta angle, it is being projected and it is going to land somewhere here. Now you might be guessing from our previous lecture of kinematics that when a particle is projected at angle theta and a complementary angle, then they take the same range on the horizontal plane or on ground. So in this case, we are projecting the same particle of mass n two times, by one time at angle theta and other time at the complementary angle. So our first part of the question is, what is the ratio of kinetic energy of the particle at the highest point of motion? So that is the question, what is the ratio of kinetic energy of the particle at the highest point of the motion? So at the highest point of the motion, the velocity of the particle going at an angle theta would be some v cos theta, and for the particle which is projected at angle 90 minus theta would be v cos of 90 minus theta, so that would be v sin theta. So the ratio of kinetic energy, the ratio of Ke, if I were to say, that would be simply half mv square divided by half mv square. So it's a simple demonstration of the formula which we know, half mv square divided by half mv square. That it would be, let's say this is the particle number 1 in numerator, so it would come out to be some v cos theta square divided by v sine theta square. All the terms are common for both the bodies, so that would be some cos square theta cos theta upon sine theta. So this is the ratio of kinetic energies. Next part of the question is find the ratio of rate of change of kinetic energy up till the point they start from the bottom of the plane to the highest point of their motions. So what we have to do, we have to find the ratio of rate of average change of kinetic energy from the bottom point to their highest point. The rate of change of kinetic energy means I am going to divide the kinetic energy of both the particles with the time taken by the particle they take to reach the highest point. So let's say this is the particle, first case in which the particle has reached the it is taking angle theta, and in the second case the particle is taking angle 90 minus theta. So the average rate of change of kinetic energy. How would we define average rate of change of kinetic energy? So we would define average rate of change of kinetic energy by dividing the kinetic energy by the time taken by the particle in reaching that point. So let's say this ratio is first particle or particle number 1. So the kinetic energy of the particle at the top is v cos theta. So that would be half mv square cos square theta. So half n v cos theta square. And the time taken by the particle to reach the highest point, so that we already know, that would be half of time of flight. The time of flight for the complete particle is 2v sine theta by g, and half of that is simply v sine theta by g. Now since the other particle is simply a complementary angle, the average rate of change of kinetic energy for the particle between the initial point and the highest most point is the ratio kinetic energy by the time interval. So this would be half mv sine theta whole square divided by v cos theta by g. Simply the angle theta would be replaced by 90 minus theta, so sine theta becomes cos theta. So we have to take the ratio of the average rate of change of kinetic energy by the particle. So after taking ratio, we can write kinetic energy by time interval as simply as the ratio like this, average of kinetic energy, some expression for first particle and for the second particle the average rate. So after dividing these two terms you would get cot cube theta. So this is our question. So this is the question which we solved. Next let us do some questions on the idea of work done by a force in two-dimensional cases. When the particle is moving in two-dimensional cases and the forces are also two-dimensional, so what is the case of work? How do we calculate work done? So what formula is used? How do we apply F dot dr and so on? So the first question which we are going to take is that of a force. It's a constant force, and the displacement is also relatively simple to understand. The particle is going from 2, 3 to 4, 1. So now next question, particle is going from 2, 3 to 4, 1. So the particle moving in any general path, the force acting on the particle is given as 3I cap plus 4j cap newtons. So this is the force acting on the particle, and the particle is going from A point to some point B. We have to find the work done by the particle, work done by the force as the particle goes from point A to point B. So the first question which comes to our mind is the particle could have gone from A to B in a straight line, or it could have gone from A to B on a general path. So how do we decide about what would be the work done in both the cases? Would the work done be same in both the cases, or would the work done be different in both the cases? So we can always take about the definition of work done, or consider the definition of work done to think about this concept. The definition of work done is integral f dot dr, and when we are integrating f dot dr to find the work done, we have to take the dot product of force and dr vector, and simply when the force is constant, then what happens? If we can think about that, when force is constant, it is simply a constant term, and dx and dy get integrated. So it becomes fx into delta x plus fy into delta y. Since fx and delta x are constant, fx, delta x, fx and fy are constant, they simply come out of the integral and they do not integrate. So because of that, the expression for work done does not depend upon the part taken by the particle. So that means a very good result. Whenever there is a force acting on a particle which is constant, then it does not matter what the path is taken by the particle, because the final expression of work done is simply delta x and delta y. So it doesn't matter in the question if it is given that the particle is going in straight line or is going in some general path. We are going to simply use f dot delta r. So our displacement in this case, delta r vector, would be the final position of the particle, that is 4, 1, that is 4i minus j cap, 4i plus j cap, plus, minus 2i plus 3j. So the displacement delta r becomes 2i minus 2j cap. So this is our displacement of the particle, and like I demonstrated, that it does not depend on how the particle is reaching from point A to point B. What matters is the force is constant, and since force is constant, it is simply coming out of the integral, and we have to directly multiply. So f dot delta r would give us the work done of the particle. F and delta r can be calculated by simply multiplying and adding. So it would give us some 6 minus 8 joules of work, that is minus 2 joules of work done. So this was the question number 1. So let us move on to the next question. So next question, we have a force which is variable, which we are looking for. So this was the case when the force was constant. So we decided that okay, the work done remains independent of the path because it is coming out of the integral. What happens in this case? So the question is, force is acting on a particle. So the force is minus k xi plus yj cap. So that means the force depends upon both n xy, and it is acting on the particle in 2 dimensions. Next, the particle is going from origin to 0, to A, A. So the particle is going from 0 to A in a straight line. That is given to us in this question, and the force acting on the particle is minus kxi cap plus yj cap newtons. So we have to find the work done. Simply we will be using our expression of integral. So the work done would be minus f dr. This is our definition of work done. So this can be written as f fx dx. So that would be minus kx dx minus ky dy. This would be our expression, right? Since we are going from point A to point B, so that would be our way of integrating them. So the particle is going from origin to 0, so that's why the limits x, the x coordinate is changing from 0 to a, and y limit is also changing from 0 to a. So it is going from 0 to a and 0 to a, y is also changing from 0 to a. So after integrating, we can easily say that this would come out to be minus kx square by 2, x dx is integrated, and similarly y can be integrated from some y square by 2, it is also going from 0 to a. So what would this expression add out to be? It would add out to minus Ka square. So this would be our net work done by the particle, as the particle is going from origin to a comma a. So here we have mentioned the particle is going in straight line. So we are taking a simple integral approach. So again, one more thing, or one thing which we should have a concept of, how to have a feel for, is that the first thing which I told just now is that when the force is constant, we can simply multiply the force vector with the displacement vector and we get the work done by the particle. And why is that important? It is important because it simply comes out of the integral. So the integral becomes important, right? And that also means that we have to be very confident with our integration capability, that we can integrate an expression if the integral gets split. So how do we and what is the need for splitting integral? So that is demonstrated in our next question. So we have next question. So in that particular question we have a force y I cap plus x j cap. So this presents a very unique opportunity for us when the particle is experiencing force in x direction, that is I cap direction, and that force depends on the value of y. And similarly the particle is experiencing a force in j cap direction where the particle's force depends upon the value of x. So the particle is going from some point 0, 0 to 0, 1, point B. First it goes from 0, 0 to 0, 1, and then the particle goes from 0, 1 to point C, 1, 1. So this is how the parts of the particle is. It goes from 0, 0 to 1, 0, and then from 1, 0 to 1, 1. So if we were to draw a graph of the path of the particle, then that would be pretty easy to draw, right? The particle would be going along some first x-axis first, and then it would be going along a line parallel to y-axis from point B to point 1, 1. So how do we deal with such expressions? How do we solve such questions where the integration does not look straightforward at first? In the previous question we had integral x dx, so we directly were able to integrate it. That is a very simple idea, integrating x dx. But how would we integrate y with dx? That is not possible, that we cannot do. So how would we proceed in this question? So to do that, we just simply write the values of y when we are going along this path. That means we are going to calculate the work done in 2 steps. Just in the 2 steps, as the question has mentioned us, that the particle is going from this point to this point and this point to this point. In the same way, we will be breaking our calculation of work. So the net work done by the particle from A to C can be divided as work done taken by the particle from A to B and the work done on the particle from B to C. So as the particle is going from A to B, the limits are 0 to 1 for x and 0 to 0 for y. So since the limits are not changing in direction of y, that integral won't matter. So we can remove that integral. So when the value of x is changing from 0 to 1, the value of x is the value of fx. Since we would have to write fx dx, right? Value of x is changing from 0 to 1. The value of fx is y, And what is the value of y when the particle is going from A to B? That is what I am saying. We cannot integrate y dx. But what is the value of fx itself? The value of fx is y. And what is the value of y? That is 0. So whatever value of y there would be given in the question, you can put that value and we'll get the answer. So putting the value of fx, that is 0 over here, we would get the work done from A to B is 0. And in the same way we can proceed from B to C, point B to C. We can say work done in B to C. The value of x, again you can see the value of x is not changing. The value of x changes remains from x equal to 1, and the value of y is changing from 0 to 1. So we are taking the value of y, that means we are talking about fy dy. So what is the value of y? The value of y is now changing from 0 to 1. So it is value of y is changing from 0 to 1, but what is value of fy? So that is again the question. We cannot put value of fy. The value of fy is x. So we can substitute the value of x in place of fy. And what is the value of x? Value of x is 1. So that is y dy 0 to 1. So this would come out to be simply 1 joules. What is the value of x as we are going from B to C? That is 1. So we have substituted that particular value. Integral of dy is y only. So it comes out to be y. So 1 minus 0 becomes 0. So that means the net work done by the particle as it goes from A to C is simply 1 joules. So that is the whole idea behind this question, that we have to demonstrate that how to do the questions when we cannot directly integrate the value of force with dx, and when the particle is also taking paths, different paths, and going from initial point to final point. We have to break up the particle and then integrate it. So one useful way to visualize how to do this question can be to draw the graph of the particle and then do it. So let us move ahead. So we were talking about kinetic energy earlier. We defined kinetic energy. How do kinetic energy and work done are related? We know work done has also a unit of joules, and kinetic energy has also a unit of joules. That means there should be some relation between them. So what is that relation? Let us try to find it. So we can find that relation by use of work energy theorem. So that means if in a question you are given some kind of kinetic energy or you are supposed to evaluate the work done, or vice versa, you are given some work done and supposed to evaluate kinetic energy, then you can use this theorem. And this theorem should strike first in your mind, that you have to use this to solve that particular question. So that is the very important idea. And this is a theorem which in itself is very useful in further chapters also. It would come again and again. So what is this theorem actually? Is this something like Newton's second law or something like that? So it is more on the mathematical side of physical law and speaking in that way, but it is much more useful. So work energy theorem is a theorem which states that whenever some forces are acting on a body, one force or more than one force. Now those forces can be external force as well as internal forces on the body. There can be internal force within the body which are trying to keep the particles together or trying to split them apart. For example, a football. So for a football, we can say the gas contained within the football is trying to push the particles outside, because the gas pressure is outside, is above the atmospheric pressure, higher than atmospheric pressure. So that's why it tries to push the football cover in outward direction, and the particles of football cover are trying to keep the football in its shape. So there are a lot of forces on play. So when a force acts on a body, let's say internal force and external force. Work energy theorem states that all the work done combined by all the force acting on the body is equal to the change in kinetic energy of the body. Now this comes to like a very outlandish claim that we can directly equate the work done by the body is equal to the change in kinetic energy of the body. So how does it come out? So let's see how do we do it. So let us try to prove this theorem. What finally we are going to prove, let us write that first. We are going to prove that work done by all forces acting on the body is equal to change in kinetic energy. So this is what we have to prove, and we are going to start from some particular point. So we are going to start with the velocity vector of the particle. We are going to take two-dimensional cases. So we have a velocity vector of the particle v vector. So velocity vector of the particle of the particle we can write as vx I cap plus vy j cap. These are the velocity components vx and vy. Vx is velocity in x direction, vy is velocity in y direction. To define kinetic energy, we I wrote that v dot v we can use. That is taking dot product of velocity with itself, which gives v square only. So we have written velocity vector. Next we can write what is dv by dt vector, which we are concerned about. What is dv by dt? So dv by dt is simply dvx by dt I cap plus dvy by dt j cap. Now we are going to modify this expression, which you will be understanding later. But first let us do it, and then you will see why we did it. So what we are going to do, we are going to multiply dvx by dt in numerator and denominator by dx, and same operation we are going to do with dy. So dx multiply divide and dy multiply divide with the other expression. So we get dv by dt. So this comes out to be, now we can take dt over here. So we can divide dt with dx. So dx by dt comes out to be vx, and this comes out to be dvx by dx. So this is what you understood, right? This is also known as acceleration of x, acceleration in x direction, and this is also acceleration in y direction, dy j cap. So this is dv by dt, which we have proved up till now. So let us multiply this particular expression with the position of the particle, or change in position of the particle. So dv by dt dot dr, that is we are taking the scalar product. So dr vector, we know what is dr vector. Dr vector can be written as some dx I cap plus dy j cap. That is the particle is undergoing some change in position. And that is what we are trying to see. Some force is acting on the particle, some work is being done because the particle's position is changing. So some small work done, and how that small work done changes kinetic energy of the particle. And since we are talking about kinetic energy, we are talking about velocity of the particle. So dv dot dt dot dr, so that would come out to be some vx dvx dx. Now after taking dot product with this dx I cap plus dy j cap, dx would be multiplied with I cap. So we can directly cancel this dx with this dx. So since we have to multiply the respective I cap components, dx would simply cancel this dx. So this would simply cancel out. And in the same way, we will say this dy would cancel out this dy component. So this would come out to be vy dy. Now in the same way, if we were to take the expression dv vector, what is dv vector? So dv vector would come out to be some dvx I cap plus dvy j cap. So taking dot product of v vector and dv vector, we would get v dv vector. So this would come out to be vx into dvx plus vy into dvy. So this is coming out to be equal to this. So I can write that dv by dt dot dr is equal to v dot dt. Now what we are trying to do here actually, so as you will be noticing, now let us simply multiply the expression of mass here in LHS and RHS. Now you will be getting what we are trying to do. Before that it was not exactly making sense at what expression we are having, how this is all related to work done, right? I mean there is no, I have not even written force yet, but now you will be noticing, yes, now force is coming, right? This is force, this is dot dr, and this is work done, and this is work done mv dot dv. If we integrate something with the element of it, so we get v square upon 2, and that is kinetic energy. So we have proved work energy theorem. We just have to integrate it. So m dv by dt is nothing but force F dot dr mv dot dv. So integrating this expression, we'd get work done by all forces on the particle. Since m dv by dt is simply the sum of all external forces acting on the particle, so sum of all force acting on the particle dot product with the displacement is equal to m v dot v upon 2. So this is the work energy. So that is the work done by all forces is equal to change in kinetic energy of the particle. So let us end our lecture with this particular derivation only, and we'll be doing the questions with the next lecture. So thank you for joining and have a nice day.